And the unifications continue that as we take steps towards the standard model, which is such an incredible part of physics in the 20th century. So can you describe that unification?
So, we're sort of jumping forward here now to the 1930s or thereabout. And by that time, people had realized that there are four distinct forces that do not seem to be connected. One is gravity. Two is electromagnetism, and those are things people are relatively familiar with. But there are two other forces that only have any real importance inside the nucleus of atoms, which is why most people have no experience with them. One is the strong nuclear force, which holds the nucleus of the atoms together. And the other one is what we call the weak nuclear force, which is responsible for some types of radioactivity. And since most people don't play around with nuclei, and most people don't play around with radioactivity, they don't know what that is. But by the 30s, scientists had done enough experiments, done enough theorizing to say that there were these four forces. And that was already a triumph. I mean, in our goal for a theory of everything, we'd like to think that there is one force, which is what we're talking about, the unification. Maybe these four forces are just different ways of looking at a single underlying force. But in the 30s, that's where we were. There were the four forces. So we move ahead, and in the late 50s and early 60s, some people were thinking that maybe the weak nuclear force and electromagnetism actually were the same. So they were working on trying to bring together these two forces to show that they're connected. And it came true. They were able to show that electricity and magnetism were actually two different facets of a single force that we now call the electroweak force.
Mm-hmm.
Now, the story that you're told in articles about this, about what people have called the Higgs boson or the God particle, the story is very, very simplified, because in 1964, there were three groups with six individuals who came up with important papers talking about what's called the Higgs field. And I'll get to what that is in a minute, but the Higgs field is important. But it wasn't until 1967, so 3 years later, that Steven Weinberg and some others actually unified electromagnetism and the weak force.
Sheldon Glashow, Abdus Salam, and Stephen Weinberg successfully unified electromagnetism and the weak nuclear force, that showing that at high energies, these two forces were merged into a single electroweak force.
Right. And that was in 67. All right. Everybody talks about this thing happening in 64, but it really wasn't. It happened over quite a few years, actually. But, all right, so now what you said is true. So Weinberg, Glashow, and Salam showed that electromagnetism and the weak force at high energies were the same. There was a problem, however, and the problem is that electromagnetism has an infinite range. And we know that because we can see stars that are millions of light years away. I mean, that shows you that the range of that force is essentially infinite.
Mm-hmm.
The weak force, however, basically becomes non-existent on distances much smaller than the size of a proton.
Mm-hmm.
So that, to say, oh, they're the same, and yet one can reach across the universe and one can't reach out of an atom, well, that's just dumb. I mean, the obvious thought here is, well, we just proved that whole idea is stupid, so throw it away. Ridiculous. And that is where these ideas from 1964 came in and saved the day. So how can it be true that the electroweak force is real and electromagnetism and the weak force act so differently?
Mm-hmm.
The way that could happen is if these forces were transmitted by a particle moving from one subatomic particle to the other. In the case of electromagnetism, it's the photon. In the case of the weak force, we call them now the W and Z particles. So the idea is that Higgs and his colleagues came up with is saying, all right, electroweak force is real. The way we make it so that there is now an electromagnetic force and a weak force is the force carrying particle of electromagnetism has no mass. The force carrying particle of the weak force has a mass. And so what was done is a field was postulated, that there was this additional field that was kind of distinct from this electroweak field, and we call it the Higgs field. And the Higgs field permeates all of space. And here's the kicker, some particles interact with the field and some particles don't interact with the field. The ones that interact with the field get mass, and the ones that don't interact with the field don't have mass. And so that's the idea, is that the Higgs field gives the weak force particles mass. However, the photon laughs at the Higgs field, doesn't see it, and it has no mass.
And I should say here, going to Perplexity, the big picture view, the Higgs field is a quantum field that fills all of space and gives many elementary particles, just as you're saying, their mass through their interaction with it. The Higgs boson is the particle associated with ripples or excitations of this field. In modern particle physics, every type of particle corresponds to a field that exists everywhere. The Higgs field is one such scalar field, meaning at each point in space it has a single numerical value rather than a direction. The Higgs field differs from most other fields because even in empty space, empty in quotes, by the way, empty space, its average value is not zero. This non-zero vacuum value is what enable it to endow particles with mass.
Right. So let's talk about something a little more familiar, just to try and hang some intuition on those words.
Awesome.
All right. So right in front of us, there is a gravitational field. Now, you can't see it, but right there, check it out.
Yep.
If I were to take something, a pen or whatever, and put it there, it feels a force and it falls. Very insightful, I know. So we have the gravity field and we have the pen that has a mass, and the mass and the gravity field interact and it drops. Now, if we had another...
I have object for you.
All right, so
demonstration purposes.
Performance art. Here we go.
This is great.
This thing has mass and we drop it. How remarkable. It falls. But when we step back and think about what really happens, it's the mass of this thing and the interaction with this invisible field we see here. That's what gives this weight. Now, I have this particle here that you can't see, but it's there. It has no mass. And I leave it there. Well, since it has no mass, it doesn't feel gravity. It's still floating there. And that is really all the Higgs field is. Some particles have effectively what you could call the Higgs charge that interacts and sees the field, and other particles don't. And that is really what you read just basically means. Now, it's kind of neat because in the ordinary day, there is a Higgs field right there, and the Higgs field is not zero, just like gravity is not zero, and things will get mass. But at super high energies, the Higgs field, the strength of the Higgs field goes to zero. So whether things have mass, or whether they have a Higgs charge or not, they have no charge, or they have the Higgs charge, Higgs field zero, they don't interact, it has no mass. So that's kind of what Weinberg and Salam and Glasgow said, is at very high energies, the Higgs field is zero. Since the Higgs field is zero, the weak force particles don't feel mass, and therefore they can travel at the speed of light, just like the photon does, and everything's happy. It is when the universe cooled down after the Big Bang. It was very hot, very high energy, nothing had mass. The universe cooled, and at a certain temperature, what happened is the Higgs field turned on. And at the moment it turned on, it gave mass to the weak force particles, did not give mass to the photons. So that's what we call electroweak symmetry breaking. So it's a mouthful. But all it says is there was a moment in time early in the history of the universe at 10 to the minus 12 seconds after the Big Bang, the Higgs field turned on and particles got mass. So that's the whole idea. So this is another really neat thing. So the electroweak symmetry theory doesn't need Higgs because that only really applies at very, very high energies. But in order to make it work at low energies, you need to fix the theory. And you need to fix the theory by effectively putting a Band-Aid on the theory. Higgs theory is just a Band-Aid on top of electroweak symmetry theory. And that is the Band-Aid that fixes it because it gives mass to particles at low energy.
But how does then this Band-Aid, the field, and the Higgs boson come into play on the experimental front, on the evidence discovery front? So what is this Higgs boson thing?
Excellent. So we have never seen the Higgs field. The Higgs field is a hypothetical, theoretical thing. But that is true of most of our fields. We've never seen the electromagnetic field. We've never seen the gravity field. We've seen the effect of the field. And so all of these theories are now what we call quantum field theories. And that the whole idea of quantum fields, if you have a quantum field, but that field can vibrate like a drum head. And so it doesn't vibrate just exactly like a drum head, but it vibrates locally. So you can have specific localized vibrations. And those specific localized vibrations are the particles. In the electromagnetic field, the vibration is the photon. In the Higgs field, the vibration is the Higgs boson. And so what we can do is not see the field, but we can actually excite the field, make it vibrate, and detect the vibrations.